So for part A, they want us to find the value of k, positive value of k, so that the slope of the tangent line to f of x at 0 is 6. So that part should be pretty straightforward. First, you just need to find f prime of x, and since that's the slope of your tangent line. So this is just a reciprocal rule. It should be the opposite of the derivative of the denominator, which is 2x minus 2, over the denominator squared. And we want the slope of the line tangent to f at x equals 0 to equal 6. So we want f prime of 0 to equal 6. So we'll plug in 0 for our x's, which is going to give us a positive 2 in the numerator. And in the denominator, it's just going to give us k squared. So we just got 2 over k squared equals 6. That'd be k squared equals 1/3, or k equals the 1 over the positive square root of 3 would be negative also, but it says k greater than 0. Hopefully that part was pretty easy. They gave 1 point for having the denominator of f prime correct, 1 point for having the rest of f prime correct, and 1 point for the answer. So that was a pretty easy part. Part A should have been pretty straightforward. Now for part B, starts to look a little bit different. Part B, we got k equals -8. We want to find the value of the integral from 0 to 1. So effectively, all we're doing for part B is just looking at this integral 0 to 1 of, what it's become, was it 1 over x squared minus 2x minus 8, I think. And so then we'll look at that and say, well, there's not really a nice, easy way for us to go about that integral without doing a partial fraction decomposition of it. I mean, we could definitely come up with some other ways, but partial fraction decomposition is probably the easiest. So we'll just first off note that this factors to x minus 4 and x plus 2. And we would see that both the discontinuities are not on our interval, which is an important thing to check, because if one of those discontinuities is on our interval, then it's an improper integral. But since 4 and -2 are not on that integral, this is just a regular partial fraction decomposition one. So we're going to say 1 over x minus 4 times x plus 2 is equal to a over x minus 4 plus b over x plus 2, which is going to then give us, if we multiply by x plus 2 here, we're going to get 1 equals ax plus 2a, and then plus bx minus 4b. And we've got a plus b x's should be 0, and we've got 2a minus 4b has got to equal 1. And so we'll just go through and solve that. We can make this 2a plus 2b equals 0. And then we can subtract, giving us -6b equals 1, or b is -1/6. And if b is -1/6, then a ought to be +1/6. Everybody good so far with the partial fraction decomposition there? Hopefully so. So a is 1/6, so we got 1/6 of x minus 4, and then we got minus 1/6 dx plus 2 down here, dx, and now we just integrate. We can pull the 1/6 out if we want. We got 1/6 natural log absolute value x minus 4 minus natural log absolute value x plus 2. And we're going to go from 0 to 1, and we'll just evaluate. So we got 1/6 natural log 3 minus natural log 3. and then minus natural log 4 minus natural log 2. And obviously natural log of 3s will cancel. So we end up with 1/6, and then natural log of 4 minus natural log of 2 is just natural log of 2. And so this becomes negative 1/6 natural log 2. Any questions there with that? And you got 1 point for doing the partial fraction decomposition correctly, 1 point for getting the correct antiderivative, and 1 point for the correct final answer there. Hold on 1 second, I gotta let my dog in. Yeah, sorry about that. Anybody have any questions with part B? Everyone's good there? Sure. All right. So for part C, it's asking us to give us a k equals 1 value and then find the value for the integral from 0 to 2. So we should then be looking at the integral from 0 to 2 of 1 over x squared minus 2x plus 1 dx, which we can rewrite as 1 over x minus 1 squared, because that's going to make that integral really easy to do. And we'll note when we look at that this has a discontinuity at x equals 1, and 1 is a vertical asymptote of x equals 1, infinite discontinuity, and that's within our limits of integration. So when we do this integral, we've got to separate it out into an integral from 0 to 1 of 1 over x minus 1 squared plus an integral from 1 to 2 of 1 over x minus 1 squared dx. And then we'll have to replace the 1's in both of those integrals with some other variable, because we've got an infinite discontinuity. So we're going to look at, let's call this the limit as a approaches 1 from the left. As we're going from 0 to 1, we're going to approach 1 from the left, and then it should be an integral from 0 to a of that same thing. And we'll add to that a limit as b approaches 1 from the right of the integral from b to 2 of that same thing. Everybody good with that, the setup for the improper integral? Okay, and then to integrate 1 over x minus 1 squared, that's just u to the negative 2 du, right? Because this is, if I let u equal x minus 1, du is just dx. So that should just become negative 1 over x minus 1 for each of those. So we're now looking at the limit as a approaches 1 from the left of negative 1 over x minus 1 from 0 to a, plus the limit as b approaches 1 from the right of negative 1 over x minus 1 from b to 2. Everybody good there? So we got the limit as a approaches 1 from the left, negative 1 over a minus 1 minus negative 1 over negative 1, and then plus the limit as b approaches 1 from the right of negative 1 over 2 minus 1 minus negative 1 over b minus 1. And if we take a look here, if we're going to go ahead and plug in as we approach 1 from the left, this part right here, -1 over a minus 1. If we're plugging in something very close to 1, this is going to become 0 in our denominator, which is going to make this integral infinite. We've got an infinity right here, and so immediately we can just say that this whole thing diverges. Good or no? And the breakdown there was 1 point for properly setting it up as an improper integral, 1 point for taking the antiderivatives correctly, and 1 point for diverges because this part of it was infinite. Cool. All right, hopefully that wasn't too bad. Anybody have any questions on that? All right, let's take a look at the next one. So this one throws in a little bit of series stuff as well. It's also got an improper integral in it, and it's got some just regular, easy, basic calc stuff. So I'll give you guys 15 minutes to work through this one, and then we will talk about it. Ready, go. For part A, we want the slope of the line tangent to the graph of f at x equals 3. So that's just a matter of taking the derivative of this. F prime. This is, again, just the reciprocal rule, so negative, and then keep the constant. Derivative of the denominator, 4x minus 7, denominator squared. And we want to evaluate that at x equals 3. So that's 12 minus 7 is 5, so that's negative 15 in the numerator. And let's see, that's what, 18 minus 21 plus 5 is 2 squared out of the 4, negative 15 fourths. And they were kind enough to give you 2 points for getting that value for some reason. All right, part B asks us to find the x coordinate of each critical point of f in this interval. So critical points will occur when our derivative is 0 or when our derivative is undefined. And so if we take a look at the numerator of our derivative, that'd be 4x minus 7 equals 0, x equals 7/4. So that is 1. And then looking at the denominator, we'd say 2x squared minus 7x plus, well, actually, we don't even need to bother with that because 2x squared minus 7x plus 5, anything that makes that 0, which, offhand, I don't know what that is, but whatever it is, we'll also make this 0 in the denominator, which means that the function won't be defined at that point, which means that there are no other critical values. You can't have a critical value at a point where your function isn't defined. So our only critical value is 7/4. So all we gotta do is make a sign chart. We'll pick something that's more than 7/4, but less than 2.5. So something like 2, and plug it in up here. We get a negative in the numerator, and we get a, let's see, minus, it's going to be squared. It's going to be a positive no matter what. So we get a negative over a positive. So our function decreases, and then plug in something less than 7/4. The denominator is still going to be positive. We plug in like 3/2 here. This gives us 6 minus 7, which is negative times negative, so a positive, which tells us that we have a local max, or relative max, at x equals 7/4. And did it ask us to find the actual max? No, just classify the point. Perfect. So that was worth 2 points, 1 for getting x equals 7/4 and 1 for the classification with the justification. Yeah, 7/4 is the only critical value because critical value only occurs when the derivative is 0 or undefined at a point that is defined on the original function. So our numerator is 7/4. That's the only thing that makes the derivative 0. And our denominator, even if you go about and solve this, whatever x value makes this 0 in the denominator here also makes the denominator of the original function 0, and you can't have a critical value or a critical point at a place where your function is not defined. Does that make sense, Shayla? Okay. And yeah, Molly, the sign chart is good enough justification there. I should put something in here that's like this is, sign chart for f prime, but yeah, that should be good enough. If you want to be extra good about it, you could write f prime goes from positive to negative, therefore f goes from increasing to decreasing, but there are no endpoints to this interval, Molly, so no, you do not need to check any endpoints. And I mean, it doesn't say anything about looking for all maxima or minima. It just says classify each critical point as a max or a min or neither. So even if it did have endpoints, you wouldn't have to bother because the endpoint's not a critical point. So. All right, everybody good there with part B? All right, part C, they've done the partial fraction decomposition for you already. That was nice of them. So we want to evaluate the integral from 5 to infinity. So we're just going to use the partial fraction decomposition to do this as an improper integral. We'll note that x equals 5/2 and x equals 1. Neither of those values fall on this interval, so it's just one single improper integral. There aren't any places in the middle that we have to break it up. So we'll do the limit as a approaches infinity of the integral from 5 to a. Hopefully I had this right. I think it was 2 over 2x minus 5 minus 1 over x minus 1. If that's wrong, let me know. That's what it said. Okay. And then we'll just integrate these. So the integral of 2 over 2x minus 5, we can do u equals 2x minus 5, and du is 2dx. The 2 goes away. That'll just become the limit as a approaches infinity of natural log absolute value 2x minus 5, and then minus natural log absolute value x minus 1. And we'll evaluate that from 5 to a. And since this is a natural log minus another natural log, we can evaluate this much more easily by rewriting it as a single logarithm. And now, as a goes towards infinity, well, actually, let me write it out. I should write it all the way out. Limit as a approaches infinity, natural log of, and the absolute value is sort of insignificant, right? Because a is going to infinity and 5 is going to make both the numerator and denominator positive. So that thing's always going to be positive. So we got natural log of 2a minus 5 over a minus 1 minus natural log, there we go, minus natural log of, what is that, 2/4? No, 5/4. I can do subtraction. 5/4. And as a goes towards infinity, this first piece here should just be approaching 2. So this is natural log of 2 minus natural log of 5/4. And if you want, you could do 2 over 5/4 to make that natural log of 8/5. But you don't have to do that. And that's that for part C. Any questions on part C? 1 point for the right antiderivatives, 1 point for the limit expression, 1 point for the answer. Actually, I think this point is probably associated over here for this expression, but good with part C? All right. And part D, we want to determine whether the series from n equals 5 to infinity of this same thing, 3 over 2n squared minus 7n plus 5 converges or diverges. And there should be pretty easy way to do this one. So oftentimes, and I've seen this a couple times in like multiple choice, they'll give you like one like this and want you to show that it converges or diverges, and the integral test will be the easiest way to do this. Remember that the conditions for the integral test are that the function has to be positive, it has to be decreasing, and it has to be continuous. So since that is true for n greater than, well, we'll just say for 5 to infinity, which is what we're looking at here. That's true of this thing for everything from 5 to infinity. If I plug in something, it's always going to keep getting smaller because this denominator is going to keep getting larger. And it's always going to be positive because this squared, once I get to 5, 5 squared is 25 times 2 is 50 minus 35 plus 5, that's positive. And every other value I plug in here, the squared will outstrip the 7n, since I have the 2 in front of it. And it's going to stay positive. It's going to keep decreasing. And it's definitely continuous because the only discontinuities we found here were at 5 halves and 1. We can say that since the integral converges, the series converges. And that is good enough right there for that one. That would give you both points. You could alternatively just use a direct comparison test if you wanted to. So we could say that we're gonna do direct comparison with 1 over n squared, and we choose 1 over n squared because if you look back at this, that's effectively what we've got here, right? We've got 2n squared. We break this down without all the constants, it's 1 over n squared, right? And we know that 1 over n squared is positive. We know that our thing is always positive. And our terms are always positive. What was ours? 3 over something? 3 over 2n squared minus 7n plus 5, I think, was also positive. And we should then just do a direct comparison and say that the limit as n approaches infinity of our series over this one should equal, if we flip around the n squared, this is 3n squared over 2n squared, comes out to be 3 halves. So since this limit exists, And we know that the sum from n equals 5 to infinity of 1 over n squared converges by the p-series test. Our series also converges by direct comparison. Or not direct comparison, sorry, limit comparison. I don't know why I said direct comparison over here. I did limit comparison because I wrote it out as a limit. You cannot do the nth term test. The nth term test can only prove divergence. The nth term test does not prove that something converges. The nth term test only says if the limit as n approaches infinity is not 0, it definitely diverges. But it doesn't say anything about using the limit as n approaches infinity equaling 0. So like if the limit as n approaches infinity equals 0, that does not necessarily guarantee that it converges. And there are tons of examples of that. For example, the harmonic series 1 over n. Does that make sense, Shayla? Okay. Any other questions on that? Yeah, you could use direct comparison, Delphine. And yes, Mahika, I can go back to part C. Was this part C? I think this was part C. Yeah, and so are you good now there, Mahika? Okay. Yeah, so Delphine, you could have also done direct comparison here. That'd be totally fine as well. From 5 to infinity, both of these series are positive, so that meets the criteria for the direct comparison test, which we'd already said here for the limit comparison test. And then we know that from 5 to infinity, let's see, actually, let me think about this. 5 to infinity, our denominator here would have been, what would that have been? This would have been 3 over 20. Yeah, actually, yeah, we still could have. We just would have had to choose a number larger than 5 because 3 over 20 is not less than 1 over 25. So you would have had to find an n value here that made this always less than this. Let's see, if I put in a 6, that'd be 3 over 35. That wouldn't do it. If I put in a 7. Yeah, actually, I don't know. You'd have to find a pretty large number for that. So I don't think direct comparison would have worked real well here because you have to make sure that this one is always less than this one. And so, like 3/20ths is not less than 1/25th and so on. So, I mean, it's possible that you could have found an n value that was large enough that would have worked out. I don't know offhand, no. Well, actually, we could figure out what that was. We would want, if we wanted to figure that out, since we're not going to have time to do another one anyway, we could figure that out by saying we make this a 1, so we divide this by 3 in the numerator. In fact, I'll do this on another page. I have 1 over n squared, and I want it to always be greater than or equal to 3 over 2n squared minus 7n plus 5. So I can multiply this by 1/3 and this by 1/3 to make this 1 over 2/3 n squared minus 7/3 n plus 5/3. And if you want 1 over n squared to be greater than or equal to 1 over 2/3 n squared minus 7/3 n plus 5/3, then you need to make this denominator 2/3 n squared minus 7/3 n plus 5/3 has to be greater than or equal to n squared. And so you'd subtract the n squared. Well, it'd probably be easier if you did it the other way. You'd get 1/3 n squared plus 7/3 n minus 5/3. If you subtract all of those over here, it's less than or equal to 0. Multiply it by 3. You have to figure out when n squared plus 7n minus 5 is less than or equal to 0. Which, you know, you're not going to be able to do that part without a calculator. Alice, could we have just directly compared it to 3 over 2n squared? Does it have to be 1 over n squared? No, you could have, yeah, I mean, you could have done a direct comparison with a different function, but it wouldn't have worked out without having to figure out this n value for 1 over n squared. So if you wanted to do it for 3 over 2n squared, that'd be fine. Let's see. I didn't write that. There we go. 3 over 2n squared as n gets larger, this denominator is going to get smaller. And so if our denominator is getting smaller, then that makes our fraction getting larger. So actually that wouldn't have worked very well either, actually. 3 over 2n squared compared to 3 over 2n squared minus 7n plus 5, because as n gets larger, this would actually be getting to be larger than this would be as well. So it looks like direct comparison isn't going to work out super well unless you can go in and figure out when something like this is true. Which, I mean, this definitely has solutions to it, so you can find n values that makes that true. But it's just a lot more of a pain than either of these other methods. Hopefully that makes sense to everybody. All right, that's where we will stop today.